Hello everyone, my name is Danila. Uh, Today I'm gonna talk about C++ best and worst performance features, and we'll talk a little bit about what we can learn from it, what the best practices are, etc. So in the slide you can see my email. You can reach out to me anytime you like, and also Telegram after the talk if you want to talk to me about C++ and whatever stuff you want. So a little bit about myself. I worked at Yandex. It's like Russian company on core search engines for a couple of years. I've been mostly responsible for performance, scalability, all that stuff. Now I'm working at Google on distributed data processing, MapReduce, data flow, Flume, all that stuff. My primary expertise is C++, low-level design, and distributed systems. So today we're going to talk. So let's talk a little bit what the talk will be about today. So first of all, we will mention and answer the question: is C++ about performance? For some of you, it might be obvious. For some of you, might not be. We'll talk a bit about not a bit, but a lot about performance problems like ABI problems, compiler problems, also algorithmic ones. And then we'll end, and during the talk, we'll talk about what the best experience across several companies that I've seen, and I don't know, that is like what companies do to mitigate some problems. So C++ actually is performant, of course. It's because of philosophy that states like in the language, that is stated in the language. So maybe you heard these 2 points many times, but still, like what you don't use, you don't pay for. What you do use, you could not hand any better. But unfortunately, this was a lot of times proved to be maybe even wrong. So I highly recommend you seeing the talk from like my colleague Chandler Caruth on CPPCon like previous year, who is talking about like there are no zero cost abstractions and everything has its cost, even performance cost. For example, he mentions that a standard unique pointer also has costs, and we don't particularly understand sometimes the overhead of even simple containers. What is standard library? Like I just briefly mentioned, just standard library provides like some standard things, which, for example, stat vector, stat unique pointer, that are very comfortable to use. Also, standard library sometimes implements some more complex things, for example, like stat shape pointer, and for example, the implementation is hard to use. And the implementation is hard to, like, the implementation is really complex. That's why that's why it is implemented and is recommended for usage in standard library. So then we like come into the real world and ask the question: is standard library like really performant? And the answer is complex, of course, but and I would say that mostly yes, but sometimes no. Let's dive. People are discussing a lot that like is C++ really performant. So I just on this slide I just briefly mentioned some issues that were raised in the past, or like even right now, that people don't particularly like, people like writing some things that are faster than standard library provide, and then I don't know, they get a lot of attention. And what this means is actually that people do care about performance in standard libraries, and that's okay. C++ is about performance, and people expect it to be very fast. What like standard library, of course, has problems, and this was proven by many people. And what it resulted in self-made libraries in different companies. Actually, I believe even if you have at least moderate project, you should have some utility library for yourself. And for example, at Google, we came up with AppSale, which provides the guarantees for across different standards. For example, you can use ABSL optional, like even in C++11, and optional, and like AppSale does not guarantee ABI compatibility, which we'll talk a little about later, and that might result in better performance. So Facebook came up with Folly, EA came up with EASTL. So, and these all happened because they don't provide ABI compatibility, at least they don't promise to. It's faster to progress in self-made libraries, and of course, if you talk about performance, you talk about like simply money, because the less CPU cycles you spend, the less you pay. So now let's dive into details. I came up with some containers that, in my opinion, and in opinion of like many C++ experts, are really outstanding. And we'll talk a bit at what cost they are outstanding and why they are good. And I could say that, for example, standard array, standard optional, atomic, string viewer, and many algorithms are encouraged to use in many places, with some caveats, but still, like everybody defaults like to these containers. So then there is another type of containers or types that are actually debatable. People still argue if standard vector is the best that the humanity can provide. Is standard string really good? Should we have small string optimization? Should be copy on write string? Like standard set, standard map, which based on the red-black tree, and no one knows if red-black tree is like better than some other trees like B tree, etc. People still debate, but from what I see, people sometimes companies sometimes don't change the implementations of these standard containers because of readability costs. Like people come into the company, and if they have different implementation of vector, they need to educate people to use different types. And standard library also is one of the things that like standard library is taught like in universities, in like courses, and it's simply like educational cost when it comes to like using something another. And of course, there are bad types and containers. For example, we'll talk today a bit why stud pair, why stud tuple are not actually what you think, I believe. Of course, unordered containers like hash maps are like very debatable, sure, but it was proven that they can be outperformed by 10x factor. And standard regex, which is, in my opinion, a bit a disaster in C++ standard. And for example, last two are banned in many places, and I don't know, each moderate project use their own implementation of hash maps or like regex libraries. So let's first talk about something simple. For example, standard array. Why is standard array so performant? The key answer is that it has zero constructors, and it follows the rule of zero. This is like I believe this is a piece of art in some sense, because it doesn't have any user-defined constructors, destructors, wherever. The compiler generates everything on its behalf. So, and the performance of standard array is the same as the C array, and with some convenient helper functions like .data, .size. So, for example, as you can see on this slide, standard array, standard array is trivially copyable type, for example, and you can when you copy like the vector from array to a vector to array, it calls like very high performant functions like move. This happens because standard array is safe to copy in this way. And memmove is a function that is very highly platform optimized. So that's why it is like truly fast, and you can't do anything better, at least like thinking about it like in some small time. So, and this leads us to trick number one, which I organized in some bullets. So if possible, make your type trivial. Trivially destructible types are very good because they allow to reuse like the object. We'll talk like the next slide a bit about it. Trivially copyable types can be mem copied, and mem functions are C functions that are highly platform optimized. So you can benefit from your CPU the most in this case. So why should you make your destructor trivial if possible? It's because of the ABI specification. So if you have a non-trivial copy constructor or non-trivial destructor, it is passed by invisible reference. What it means, let's see the example. If you have a class foo with some default destructor and class bar with some user-defined destructor, even if it's empty, when you try to copy and to pass like the object by value, which is reasonable in this case because the objects are small and small objects should be passed by value. And you can see that in the first like class foo generates only one instruction when it copies because it stores in like EDI register, but when as user defined destructor it has like an invisible reference. For example, standard optional is follows this rule, and as you can see, when you pass like standard optional by value, which is reasonable in that case because it's like only 8 bytes at most. So you move like the registers and do the shift to like know whether it has value or not. And let's see, and standard optional is a bit tricky class, and let's see how it optimizes and how it is optimized in the standard. So in the standard draft, it says that the destructor of optional, if the underlying type is trivially destructible, then this contains a value and the destructor is called. If the type is trivially if the type was not trivially destructible, if the type is trivially destructible, then the destructor is trivial and it does nothing. So in the previous slide, you can see that as the destructor is trivial, so then you should not you do not pass the optional by reference, and in that case, it is as performant as standard pair of type and bool. So, but how is it achieved? So optional, like performance of optional is very is a very complex thing. So you need, first of all, to dispatch somehow or to partial specialize somehow optional to call the destructor on non-trivial types and to default to trivial destructor on trivial types. And here I mentioned like the class hierarchy of the optional. So optional first inherits from optional move assign base, from copy assign base, move base, copy base, storage base, destruct base. And all these classes have partial specializations for if something is trivial, if it's trivially move assignable, if it's trivially copy assignable. So, and in the end, we have optional destruct base, which we were talking about, and it has also a partial specialization if type is trivially destructible or not. Why like this design is clearly complex? Why do we have this kind of design? Unfortunately, we cannot have partial specializations on special member functions, so you cannot do any kind of sphenae on or anything like that on member functions until C++20 actually, and we'll talk a bit about it later. So, and optional performance optional is performant, but the implementation is like 1400 lines of code, which is actually, in my opinion, it's like huge. So, and also I'd like to say that it was not always the case. So until it was not the case until the proposal of triviality propagation to standard variant and standard optional. And for example, this was a bug in GCC in libstdcxx for until like the 7th version, that standard option, the construction of standard optional is more expensive than the pair of the type and the Boolean flag if the type is like present. Yeah, so we talked a bit about that optional is performant, but it pays a lot for its design, and the implementation is really huge. Unfortunately, standard pair and standard tuple appeared before C++17, and they actually, like, standard pair was designed like in C++9, even 98. And as you can see in this benchmark, I am copying like I have a struct my pair that has two integers, and I have like a vector of 100,000 elements, and then I just copy vector 2 to vector 1. And in the later case, I copy just standard pair. And as you can see, the copying of my pair is actually faster than standard pair. And when I first saw this, I just even didn't realize that this is true. But unfortunately, standard pair has its costs. And why? Because standard pair overloads the assignment operator. So it has like a conditional on the type argument type. So if the first type and second type are copy assignable, then we can define a assignment operator. And underscore NAT, it is like a acronym for not a type. It is like an empty type, and it defaults to like something non-existent if the types are not copy assignable. Some people can think that, hey, this can be replaced by is equal to default from C++11, but unfortunately it cannot, because this implementation allows standard pair to be constructed for references. And yeah, you can create standard pair for references and assign one standard pair with reference to another standard pair of reference and change the according memory locations where in this example, where these integers point to. Yes, defaulted copy assignment operator is defined as deleted if the type is a reference type, unfortunately. And this makes sense at some point because when you have a reference, you don't want to, and the assignment of a reference is actually the assignment of an object rather than the assignment rather than the assignment of a pointer. So that's why it is deleted. And yes, you can fix standard pair at some point by dispatching the implementations for if it's a reference or not, but unfortunately it is not possible right now, and we'll talk a bit about later. Good news for standard pair, by the way, that it tries to be highly optimized from the compiler perspective, and if you create a pair of two underlying types of 32-bit integers, you'll have like this in 64-bit integer. This is at least something, but for example, for tuple, this is not true. Tuples just have to move instructions in that place. So compilers try to somehow trick the implementation, trick the implementations, trick the guarantees. But unfortunately, there is a very scary word called ABI, even it's 3 words, application binary interface. And all these changes, if we have a default copy assignment operator for standard pair, this will break an ABI. And let's talk a bit about an ABI. What is actually an ABI? Because many people don't quite understand what this is about. So ABI, if briefly, it is a translation unit interaction. So if we have one translation unit, we have another translation unit. So how do they interact? For example, if you change something and ABI ABI break is an entity that if you that new code becomes incompatible with like old code. So new translation units are not compatible with old translation units. So if you change the Mangle name of a C++ function, then it is an ABI break. If you add some template, this is an ABI break. If you change the number of bytes that the type contains, it's an ABI break. If you change the binary representation, ABI break. If your destructor was user defined and then it became default, it's also an ABI break because it's register level calling conventions. So in standard library, they try to preserve ABI in order to be able to compile old libraries with new standard library, but unfortunately, this comes with some limitations. And in this example, in like standard pair, what we see if we have two integers and a user-defined assignment operator, do we have a default assignment operator? This results in and we have two functions, for example, example one copy and example two copy that simply just copies like e other to e to e other. And this results in that we have if we don't have any optimizations, it results that example one has a like assignment operator defined, but example two doesn't have. So if you change the copy assignment operator to default, your old code will not be compatible with the new code because it just will not have assignment operator. This is happening because for trivial types, compiler might not generate any assignment operators or special member functions in its binary. So yeah, you cannot change like this is an ABI break. Fortunately, this is a very lightweight ABI break, I could say, because any decent compilers with any optimizations enabled inline the copy assignment operator for trivial types. So it might be okay in most places if we break something. But and in the future, I believe we will have a conditional trivial member special function. So if you have some concept, you can define that the copy constructor, copy assignment operator is default if it satisfies some concept and something other in the other case. And for example, the authors of the proposal showed that optional implementation goes down to like 390 lines of code, which is still fair amount lines of code, but not 1400. Okay, so this leads us to trick number two, which is somewhat connected with trick number one. Always write is equal to default in your code, always when possible. If you have some even standard types in your class, like write is equal to default. Yes, the special member functions will not be trivial, but if you change the code, it might be beneficial for you in the future. Now let's talk a little bit about some debates. For example, standard string. It has been discussed, I believe, a lot since C++ was evolved. So you have like for standard string, like most implementations use so-called like small short string optimization. It is basically standard string must contain pointer, size, and capacity somewhere. And small string optimization says that we can store small strings in place in these bytes. So, and actually, I quite failed getting who was the first to invent this thing, but likely someone dates back to 2000, 2001. So small string optimizations, like in libc++ with like 64-bit, I'm assuming 64-bit architecture, like maybe even little endian, or doesn't matter at this point. So libc++ has 22 bytes because you have data capacity and size, which like all must be like of 8 bytes, and 22 bytes because you need 1 byte for like the last character \0, and you need somewhere to store the size. libstdcxx has 15 bytes of small string optimization. Actually, libstdcxx size of string is actually 32 bytes. They store one additional register in order to access the size without any branch. Microsoft STL like uses the same technique as libstdc++. FB string uses 23 bytes, and I highly recommend watching like the talk about how FB string is implemented. And yes, some other companies, for example, as Yandex in its utility library, they like tstring has 0 bytes, and it's fully like copy on write. Is it, I don't know, like different companies, different vendors choose different implementations, and that's okay. So briefly, how standard string is optimized in libc++ to understand this better. So we have capacity, size, and data, and we have one least significant, like, and we have 1 bit in least significant byte of capacity, which can be set to 1 if the string is big, and set to 0 if the string is small. So if it's big, it is set to 1. If it is small, it is set to 0, basically. By the way, it is set to 0 when it is small in order to construct standard string, default standard string with like a couple of instructions that just 0 the registers. And if you have like yes, and the small string is represented in these like 24 bytes like this. What is fascinating about standard string that other types also use the same techniques. For example, standard function uses small object optimization. So if your function pointer, like if your lambda or I don't know any object with operator parents like is small, it can be inlined and might not allocate memory. This trick is really useful for highly access data. I could say it has some costs of course, it has some costs for example, for a branch. If you want to access the size of the standard string libc++, you need to pay branch. You need to understand whether the string is small or big. Also, standard string standard string like owns the data, and it's actually true that a lot of people are still like writing const standard string, mostly because the class called string view was not implemented until C++17, and string view is basically just 2 pointers, like the start and the end of the strings. And standard string view is good because of tricks first 1 and 2. Like standard string view doesn't have any indirections. It's a very cheap copy. It's only 2 registers. You must pass it by value. And yeah, it's just it's standard string view is a trivial type. So, for example, if you want to access the size of the string in libc++, you need to pay branch, as I already said. So it's a check for if the string is small. But if you have a standard string view, the size is just simply the move of 1 register. Yes, standard string view has some cost when constructing from standard string, but if you have a cascading parameter passing, it is better to pass standard string views because you don't need to branch many times if you access, for example, .data, .size a lot. Standard function, also this, for example, this I've seen a lot. If you capture by reference by default, you'll have some problems because of small object optimizations. If there are like many variables in the scope, so you need to have some sort of references to all these variables, and compilers and not always optimizing away all the unused variables that you use in Lambda. So this leads us to trick number 3. Use standard string view and standard span. Standard span is actually the same as standard string view, but for all continuous containers, almost everywhere. So if you have passing like const standard string reference, replaces with standard string view, you will see the benefit in a long run. And the trick number 4, which I was talking a lot, remember about small object optimizations. Don't capture blindly by reference in Lambda. This is kind of important because highly accessed data or like high statistically small data is really a common case in many places, I could say. So remember about this and don't be fooled. Also, standard string has some other different problems. For example, in this example, assume that vector to join has some field members inside it. So if you want to join all the strings into one, you need to like add, for example, this for loop, and this for loop will result actually in linear allocation, each time allocation, because you need to allocate, because when you're like concatenating into strings, you need to allocate enough memory and then copy the right hand side to the left hand side. Unfortunately, that results like in O big of n allocations, and but you can do better. You can do, for example, you can compute the sizes of all strings that you are going to join, allocate only once, and then just copy all the strings byte by byte. And this like will save a lot. And unfortunately, standard library doesn't have these helper functions. The situation will be improved a bit with standard format in C++20, but until C++17, it is not the case. That's why actually all libraries that I've seen that try to be like the complementary to like standard library implement something like string join. For example, in the EASTL, it's called str join. In Folly, it is called Folly join. It sums all sizes, does one allocation. Also, it has some trick. All like many implementations, at least libc++ and libstdcxx has the hidden function called underscore resize default init. So it resizes the string up to a certain point. Like it resizes the string with the value it passes, but it does not guarantee that all the characters in the string will be zeroed at this point. So it's like a cheap resize. So just one allocation, that's it. It is better than reserve, because when you reserve some memory to a string, and when you concatenate all other strings, you need to check whether you have enough capacity, and compiler cannot sometimes optimize, or maybe always cannot optimize, that this condition can be removed. And with this resize, you basically can resize once and then copy a string one by one. So actually, even in C++20, the situation is not like better, is not much better, and I kindly suggest you to write your own string operations library or use the existing external one. This also will save a lot for you like in the future. Don't write for loops when you concatenate string one by one. Another debatable thing are like unordered containers in standard library, and unfortunately, this also a big pain because standard container hash maps can be outperformed by 10x factor, and basically you cannot fix the unordered container implementation much, because users got used to some invariants, for example, pointer stability. When you erase the element from the container, all other iterators are not invalidated, and this and this was shown that this is needed like for very small percentage of users, but still this is needed, of course, in some cases. And in C++ 17, like unordered containers still does not support do not support heterogeneous lookups. So basically, you cannot look up by string view to find some strings to find in the unordered map of unordered set of string. So many, like, I believe that if your project is at least of moderate size, you already wrote some hash hash table or use the external one. And yeah, for example, you can see a link. This is a good benchmark from Google that provide many hash table benchmarks, and they like show which containers are the best. Actually, Google decided, maybe, and for a reason actually, that flat hash maps are one of the best choices for almost for everyone. So if you have enough hash table usages, use external ones or even write your own. This is what I've learned, and this is true. And hash tables I use like almost everywhere. So let's talk now a bit about algorithms. So algorithms, unlike types and containers, don't have many ABI problems. For example, algorithms try not to use any memory, try not to use any even external memory or even like some state, because that way they cannot be optimized in the future, they cannot be changed in the future because of the ABI problems. And they are actually, from what I see, they are constantly optimized. So new algorithms come, some SIMD, like loop unrolling, like is improved or something like that. Also, compilers produce better SIMD code with time. That's also true for many containers. For example, if you fill the container with 0, it will try to, for example, stat vector of int with 0, it will try to call memset in most cases. And in algorithms, there are only several still debatable on how to implement things. For example, of course, this is the standard sorting algorithms, like some nth element, and not many out of them, but I still recommend use them because they are good. They are improved with time, and they have like zero like readability cost, because people definitely, when they learn C++, they definitely will learn that there is a standard sort in the in standard library. Let's talk a bit about like some non-trivial algorithms and how they do their best. For example, there is an algorithm standard rotate. Basically, it just rotates the array with some by some index. So like the kth index will become the first one, and the kth minus one will become the last one, and they continue and it's like a ring. So it's like rotates a ring and gets the vector of rotated elements. So basically, there are two algorithms that compete with each other. It's like so-called GCD rotate. Somebody may know this algorithm is called like juggling algorithm, where you split the input range by greatest common divisor of any k elements and just rotate one by one in these groups. So, and it moves like n plus greatest common divisor of n k times, but it requires random access, unfortunately. And there is an algorithm forward rotate. Just basically, you have 2 pointers and you just move 2 pointers and swap them until you get and with some like if statements. I don't want to go into detail, but with some if statements, you just swap the pointers while you're moving, swap the iterators while you're moving them at the same time. And yeah, this algorithm, for example, provides the guarantee that it moves between 1.5 n and 3 n times. So GCD rotate is cheaper for moving. It like moves less times, but forward rotate for example, is more general because it only requires the forward iterators. What the implementations do is basically they try to dispatch the implementation by so-called tag dispatching. So, for example, iterate a category, and in libc++, if you have trivially move assignable, so you use rotate GCD, otherwise rotate forward. And if you have a forward iterator track, it uses just rotate forward with some tricks around special cases. For example, the same thing, the standard copy, DARS. Uh, yes, so if the type is trivially copy assignable, actually I believe this is a bug, but like I'll talk like in a minute about it. But if you have two pointers to copy, you just dispatch the implementation by memmove, and this is like almost the fastest thing you can provide for copying maybe overlapping pointers. Is trivially copy assignable here because mem functions require, by the way, by standard, to use mem functions, you need to require that the objects are trivially copyable, and trivially copy assignable is not the same as trivially copyable. I believe this is a bug, and I reported, I believe, this as a, but like in real world, this does almost the same. Trivially copy assignable is not affecting memmove almost in any other way. For example, other algorithm that we can consider is like standard reverse. This is the implementation from Microsoft STL, and this is actually the only example where I saw that the some vectorization is used. For example, vectorization is allowed if it is a pointer, if it's trivially swappable, it's not volatile, but yeah, just that's the detail. And yeah, this is like what's going on in like standard reverse, where the trivial type is of size 2. They try to use some very cool VX features to provide the best speed they can. So now let's talk a bit about standard sort. It also has some interesting tricks. Standard sort, and I want to point out, it must have a big of n log n comparisons, and people still debate what the best algorithms are. Some people think that intrasort are the best, some people think merge sort are the best, PDQ sort, which is like popular, which became popular in the last years, count sorts, and all that kind of stuff. For example, in libc++, there is a quadratic sort. There is a bug. Actually, it was opened long ago, and I don't know yet why it wasn't fixed. Maybe because people got used to the speed that libc++ provides for standard sort, and they cannot move out from it. But libc++ has quadratic sort only in the worst case, but on average case, it has like O big of n log n comparisons. So this is the example and the link where you can find like how to construct an example for any actually quick sort that tries to make the sort quadratic. And in libc++, this example works perfect. And for example, in that case, if you have n is equal to 1000, libc++ will do like n squared over 4 comparisons, and libstdcxx will have only like 30,000 comparisons, which is like nicer. But libc++, as I mentioned, provides some cool guarantees for some non-random containers. For example, for equal sorted pipe organ, push front, push middle containers, it is much faster than libstdcxx sort. And for random, it is like comparable, I could say. So sometimes, yeah, the algorithms might not be the best in the worst case, but can be good like in the real world data. But yeah, standard sort libc++ works like square, like quadratic in the worst case, but I still recommend using it because your data is likely not like the worst case. and it and by stats this is very hard to not this is hard by some user data to force the quadratic sort. Another algorithm I want to consider in this section is like MinMaxElement. It also has some interesting guarantees. For example, it uses 1.5n comparisons, where if you call min element and max element like one by one, it will have like 2n comparisons. So if you need to find the minimum and maximum element at the same time, and you have some big types like standard strings, whose comparison is pretty is not cheap, then min-max element can be better, but for trivial types, it can be worse. Actually, it is worse. For example, in this example, I tried to generate some like vector of random integers and to find the minimum and the maximum element, and it turned out that for integers, for trivial types, it is better to call min element and max element. But still, min max element is still good, and it is better for general case. So I summarize this trick as use standard algorithms. They are almost always good, and they are improved constantly with time. And readability cost, and they have like fewer problems than like types and containers. So highly recommend using them. Like a little bit of like just a few notes about atomic. Atomics are really good because there were a lot of debates how to design them, like on pre C++ 11, and luckily they were designed very good. So they were designed by like memory model. You can choose the memory model you want, and they are supported everywhere. They are supported on most used architecture platforms. On CUDA, you can use even 16-byte atomics. They are constantly improved with the processor progress. So like I believe in the future we can have like somewhat like 32-byte atomics and all that stuff. So use atomics, they are like really sane. And one note, volatile keyword is deprecated, and I highly recommend watching the talk from CPPCon from GF Bastian at CPPCon like 2019 about what will be deprecated in C++20 for volatile and why. This is a very good talk. And use atomics. Just please use atomics. They are really good. A little bit, let's talk a bit about disaster things in standard library, in my opinion, and in many others' opinion also. Standard regex. Actually, a little bit about history. Standard regex was designed to support a lot of different grammars. So these are like just the list of some that I provided. There are like many of them, and standard regex must save the state of the like DFA or NFA in its implementation. So all new grammars are a bit different. Like all grammars are a bit different from one another, and they all become the part of ABI, and ABI is very hard to fix in this place. So, for example, you can see that standard regex is like hundreds times slower than some other regular expression engines because of that. Also, standard regex, like in libstdcxx crashes. It has like memory corruptions, resource exhaustion, so all that kind of stuff. And these things are not fixed because of a big complexity. So regex header in libstdcxx contains like around 5,000 lines, and it's very hard to fix things not without breaking ABI that the library provided. And this leads us to trick number 9. Please never use standard regex, or just please don't. It's not what you want. Just trust me. Use You can use, from what I recommend, you can use RE2 library. Hyperscan library is very very good, like recent library that is highly optimized for x86 platform. PCRE is good. Some boost regex, by the way, is also is much better than standard regex. When we discussed about standard library, we come into the real world, and in the real world there's also a balance. True speed, the speed for the last cycle of the CPU might cost readability. So yes, you can write your own, I don't know, standard mem copy a little bit faster, maybe 2% faster than the standard implementation one. But if you wrote this, you then need to educate people that read your code. That's might be a bigger cost in the long run. So I don't recommend optimizing the last percent of the application because it might be expensive in the long run. Just try to reason about trade-offs. What will it cost? How can it be simplified, etc. That's also very important when you debug things. For example, there is some disaster happened in the code, or some new implementations can also be buggy because standard libraries are highly tested by the maintainers, by many vendors, and your implementation contains bugs with higher probability. Yes. So let's talk a bit about what in the real world happened. I often have questions about what is better, libc++ or libstdcxx, and I have two examples where libc++ outperformed libstdcxx. First example is ClickHouse. ClickHouse decided to update the standard library for GCC, and the overall performance improvement was about 2%. You can see the link, and this is it contains all the necessary steps to update the standard library. Sometimes it is difficult. Sometimes you need to spend some time, whether you relied on some behavior that is checked in one library or not checked in another library, but still, this was a win. For example, at Google, we also decided to transition our code base from libstdc++ to libc++, partially because we wanted to be consistent with LLVM and Clang, partially because we wanted to turn on C++17 in our code base, and we managed to do that. But in the end, libc++ has had 1 to 2% performance win fleet-wide, so that was also a big win. So trick number 10, which I highly recommend, write your own benchmarks, try different things, find your best combination, but don't forget about readability and the cost you pay for onboarding people, for teaching people, and so on. I was talking a lot about ABI, and the ABI breaks are not somehow allowed in standard libraries, but yeah, this was a very big concern on the latest meetings of C++ standard committee. For example, Titus Winters provided a paper that they the community is highly concerned about ABI breakages, so we cannot evolve for standard library performance if we want to better standard library performance, we need to somehow change things because some things just didn't work quite well, so we need to fix them, and that's okay. This is the real world, and in order to do this, we need to recompile, unfortunately, everything in order for all libraries to catch up with the ABI changes. And yeah, this resulted in a tough meeting in Prague. So committee, and the decision was that the committee can consider ABI breakages, but only for huge performance wins. So, for example, fixing standard regex, I believe, can be at least considered. Like C++ standard have not committee has not decided or whether we want to break everything or not, but they agreed we don't want to break much from release to release, at least not to increase the cost of the cost of developers to migrate from one standard to another standard. Yet there is a solution to this. For example, our compilers can provide some tooling, for example, to like help to migrate from one thing to another. And I believe the most important one that we should be very loud about the decision. So if we prioritize performance over, if C++ prioritizes performance, which it should do by its philosophy, then we need to be loud about the decision. But if you want to be stable, for example, like C language is very stable and has like fewer containers, fewer algorithms, etc. We need to be also clear about that we do guarantee ABI compatibility. So the trick number 11 is C++ is more than just performance, in my opinion, and I believe this is true. Always consider the trade-offs and try different things and find the best ones. So actually, that's it from me. We have 17 minutes left, and I'm open to any questions.
Thanks, Danilo, for your presentation. That was really interesting. Your research is really interesting, and the tips are really awesome that can be used in the real world. So, thanks about that. I want you to talk about a little bit more about ABI break because, as we see from your presentation, we have some small but the violation of the C++ principles, like don't pay for what you use. STD pair is a great example of that. And the committee thinks that it's not the reason to make an ABI change. So what do you think? When we will be capable to make an ABI break? So when it's the time to break the ABI?
So I believe a good strategy for this is that we have some starting point. For example, yes, we know that this is bad, and in order to improve this, we might want to break things. Unfortunately, then what we can do is like say, hey, this is the starting point where we consider this ABI is like a version of ABI. So, and we can support it for, I don't know, some years. For example, like 7, 8 years, maybe like 10. I don't know how many. And then we just break things. If you haven't recompiled your code, that's your problem. So we can notify people that, hey, we want to break things, but please recompile your code in the next, I don't know, decade for this. This, in my opinion, this would be a very good like solution to ABI breakages and to answer the question like when. So
yeah, actually, this makes sense. Yeah, thanks for that. We have another question. So you showed us the size of stud string, small size of stud string with this optimization. So what is the actual size of stud function for small size optimizations?
as I remember, it's 24 or 48 bytes. I don't remember exactly, but I believe 24 bytes also. Yeah, 24 bytes.
Yeah,
so
nice.
This is like the detail of the implementation.
Okay, so I see that. I wanted to talk about a little bit about your experience as a. I know that you help guys from Google make some performance changes in compiler and C++ library. So
Yes.
maybe if you can, please share some experience on that. So what changes did you make to improve the performance on those? If
Um,
it's not an NDA, of course.
yeah, I can talk about some things. Like LLVM is an open source, and I definitely can talk about like my submissions to it. So for example, as you can see here, there is uh, there is a PR on suboptimal code gen for standard vector of unsigned char. That was found during. Actually, this was found by me at Yandex. First, that in libc++ vector of characters is not like highly optimized. The problem was that if you construct a vector of some like number of elements, then it is basically uh, like or has a loop one by like zero in element one by one. It was not optimized to like memset or something like that. And it was very easy to fix, like some variable tricking, and it was like the LLVM problem where it like thought it's they had thought it has some strict aliasing uh, contr like contradiction and cannot optimize things, but yeah, it was fixed. It was found by me. Later, it was fixed at Google, and like I also pointed to like the maintainer of the library that some other containers do have these problems. For example, stdec. And other things I do for LLVM, I'm like more fond of like compiler optimizations, I could say. So I was uh, submitting definitely patches to fix null pointer checks. So if we dereference the pointer then is not null, and was not propagated a lot. Uh, yeah, some also like from recent things, I try to optimize 128-bit division. Um, so I'm just like trying to find things that I don't know that arise like in my in my problems and try to solve and try to understand what's like the root cause. And sometimes it happens to be like in an LVM or like in the compiler and trying to fix them.
Yeah, that's quite impressive. Do Upsale already use C++ 20 features? And the question uh, is there any significant performance gain on refactoring some stuff to the C++ 20 features, like maybe concepts or whatever?
I don't know specifically about C++20. Like the first question was, does Upsale support like C++ features? Uh, Not yet, as I believe. For example, some traits are definitely missing. Some and I don't remember if C++20 added new containers. I believe not. So Upsale didn't add anything like didn't add any version of any C++11 version of new containers. So I don't know for sure, but for now I believe Upsale doesn't support C++20. For performance gains, actually, I've seen a very good, a very good feature in C++20. It's called char-at. So it's basically it's basically the same type as character, but it follows the strict aliasing rules. And what I know, for example, ClickHouse managed to migrate from some like uh, container of characters to container of characters AT. So and it got like pretty significant performance, I believe, from 1 to 3%. So yeah, this is the performance feature that like arose in my mind.
Mhm. Um, you did talk about some C++ containers, but you didn't mention stdec. Any performance gains we can have with deck? Because that's a quite debatable container, I
Yeah,
think.
that's quite debatable container. Actually, the usage of deck is quite like, for example, stdvector is used everywhere. Stdec is not used everywhere. It is used occasionally when people like specifically need to grow in both sides. From what I know, from what I've seen, for example, Yandex patched the libc++ version of standard deck to have a bigger slice. So standard deck is basically like linked list, or like you can even say a vector of slices of some constant size. And yeah, I believe we got some performance gains when we increased the size of the block, actually, of the deck. Yes, and the deck, yeah, is not that performant, I could say. So I saw people were complaining about deck. So, and I don't remember any alternatives for now. So this is like my experience for like standard deck.
Yeah. Okay. Guys, in case you didn't join our Telegram chat, we are asking questions in Telegram. So if you didn't in our Telegram chat, so please join. It's right below. So I wanted to talk to you about the. So I think. So what's your opinion between? So I think the C++ standardization committee is constantly choosing between the stability and the performance. So, what is more important for the C++ nowadays? What do you think about that?
Um, Difficult question, I could say. So I definitely know people where the choice of recompilation, where they just cannot recompile everything, and just because, and they rely on like ABI stability. For example, Google, while transitioning from libstdcxx to libc++, this is definitely an ABI break, and this took like several like developer years to make this possible. But I believe that if C++ would not prioritize performance in several places, we would have a lot more like crunches and like self-made libraries that extend the standard library, and we might even end up in having some sort of C++ dialect where like people are okay with breaking things. So I'm quite concerned about this issue. I believe that C++ performance should be prioritized, but maybe not like in a brutal way. As I already mentioned, like 10 years gap between deprecating and removing a feature seem quite reasonable to me.
Yeah, and I don't know. That's quite sad that we have standard library which we have to replace in some cases when we want to gain performance. So, and as you said, an educational. So it's like an educational stuff is
Educational cost, yeah.
yeah. Um, so did you make any research on allocators? What's the fastest allocator?
What's the fastest allocator? Yeah, that's a very good question. I definitely tried a lot of allocators. So I had experience with Gemalloc. It's like Facebook's allocator, as I remember. Uh, it's good. It's really good. Many people are using it, and they cannot move to other allocators because Gemalloc is like the fastest one. Standard library allocator, I don't remember the the exact name, but it has the name like it's like libc allocator is a very good default in my opinion. So I have not seen people like complaining that it has some drawbacks in allocating a lot of in calling a lot of map sections and whatever. Uh, at Google, we not so long ago we published tcmalloc, the improved actually version of tcmalloc. For example, this allocator works for all Google, and this is a good, I don't know, starting point for us. So we like, I believe almost all targets and binaries are compiled with tcmalloc. There are definitely some other allocators, for example, for small chunks of data in Microsoft. Microsoft presented a allocator called MinMaxElement. It's very good for really small chunks of data. Yeah, I believe that's it. Like, I don't have actually recently I started thinking that people optimize their programs for allocators. So if you choose some default one, you'll have the best performance, and at some point if you change the allocator, you might see the like big regressions no matter which allocator you're like moving to. So people are optimizing code for allocators, and allocators are not optimizing code for people at some point.
Yeah, I see your point. So people should stick to the allocator and just try to write the code for it, and that
Or
will gain
just not to try
some
to
good
write the code,
results.
but just happens. So if some people, like, I don't know, once you wrote the code and you see the regression, you just rewrite the code a bit, and now you don't see any regression. But in other allocator, it can be definitely.
Yeah. So an interesting thing is that somebody uses copy and write strings in our cache coherent world. Like we should use atomics to use COE strings, and it could be really slow. So what's the motivation of people using copy and write strings? What do you think about that?
Um, Very good question. Uh, so, for example, Google also has ABSL chord, so it's not a string. It's actually, if it says something to anybody, it's a structure called a rope. So it's just it actually is a tree of strings and the tree is like automatically balanced. So it has like cheap adding, cheap removal, and if this is a tree, there are nodes which contain strings, and these are reference chunks. So you can have cheap copy. Like copy on write has like cheap copies when you just need to pass something and need, for example, to add or modify. So in this case, I believe it's reasonable. So if you have a cheap copy of some chunks and you, I don't know, a little bit modify like just chord, like you're adding to the end or adding to the start, and it's okay because all the chunks in the middle will be still referenced and there is no copy. Like standard string does not provide these guarantees. When you have fully copy and write standard string, I'm not sure this is reasonable at this, like in the modern world actually. So yes, of course you can have cheap copy, but you should not even pass the string by copy, and any mutation to the string will require any like size mutation to the string will require the like the actual copy of the string and the decreasing of the reference counter.
Yeah.
So in some
Yeah.
cases it is valuable, and sometimes it is not.
Yeah, so thank you. We are running out of time, and we're happy to see you in Zoom and you guys to discuss some more hot topics about C++ standard library. So please join us, and let's have a great discussion there.
Thank you very much, Danila.
Okay.
Thank you, Evgeny.